In this video, we are going to be learning about nuclear fusion and nuclear fission. We're going to be learning about some positives and negatives of each and how to do certain energy calculations of both. So let's start with fission. What is nuclear fission? Well, nuclear fission is the splitting of a large nucleus into smaller nuclei. Or in other words, the splitting of one large atom into many smaller atoms. Now, one thing with fission is normally when we have fission, more neutrons are given off, which could then cause a chain reaction and more fission to occur. But before we get into that, let's talk of where fission is used. Fission can be used both positively and negatively. In power plants, we tend to use fission in a very positive way, where we use fission on uranium to create energy. Where it's used negatively is in certain things such as atomic bombs. And we'll learn about the energy of both of these throughout this class. Fusion, on the other hand, is also both beneficial and it's been used negatively as well. Fusion is when two low-mass nuclei combine to create a larger nuclei. So in other words, we're forcing two nuclei together to create a new nuclei, and which creates energy. So where do we see this? We see this in the sun, which has many positive benefits, such as the energy from the sun gives us photosynthesis and many other things. It allows life to happen on Earth. But we have also seen it used negatively in things such as hydrogen bombs. So let's look at this example here. It wants us to complete the following reaction. But before we get to that, let's try and figure out what kind of reaction it is. I look at this, I have uranium-235 interacts with a neutron. When it interacts with the neutron, we end up getting barium-144 and some unknown element, and we get 3 more neutrons. Well, I look at this, the uranium-235 is breaking down. So that means we're undergoing a fission reaction. Well, what is this mystery atom? Well, first of all, we know my atomic mass number cannot change. My before and after must equal the same. So in other words, I'm going to have 235 plus 1, and then we're going to minus 144 minus 3 times 1, and that's going to give me a total of 89, because I took all of my atomic masses to figure out what is this one. So I'm going to have some atom with 89 nucleons. Now let's figure out what is going to be my atomic number. And my atomic number has to stay the same, because we're not going to be destroying or losing any protons. So I have 92 there and 56 here. So I'm going to go 92 minus 56 is going to end up giving me 36. Now I look up what is element 36. That is going to be krypton. So right here we're going to end up getting krypton. Now this is, like I said, a type of fission. So where do we see fission? We often see it, like I said earlier, in power plants. So how does that work? Now if I look at this here, these red bars here, these are going to be uranium-238 or radioactive uranium bars. Now, what ends up happening with these uranium bars is when one of these bars start undergoing fission, it's going to shoot off 3 neutrons. Because if we look here, we have 3 neutrons being shot off. So we end up with 1, 2, 3 neutrons being shot off in different directions. So let's draw that out here. When we draw these, we're going to end up having 3 neutrons being shot off. So I get 1 neutron shot into there, another one, and another one. And that's going to cause a reaction in this uranium rod as well. Now from here then, we're going to get 3 from this first one being shot off, and then we're going to get 3 from the next one being shot off, and so on. So we end up getting something called a chain reaction. But now here's something interesting about these nuclear reactions in power plants. These neutrons are going so fast that they actually go through and they don't react with the other uranium. So how do they make it react with the other uranium? They must slow down these neutrons. So that's when they put a graphite coating over their uranium. So when they put in a graphite coating, that's enough to slow down the neutrons so then they could react with the uranium, causing this chain reaction to occur more and more and more, and it causes the action to speed up. Now, what happens when these get too hot? Well, then we have these other metals that are very stable that drops down and it absorbs all of the neutrons that are being shot out from our fusion. So that's in general how these nuclear reactors work and how something called a chain reaction nuclear fission occurs. And it's very easy to get out of control. So the graphite or heavy water that is used to slow down neutrons in order to react with the uranium and create a chain reaction, those are called moderators. Control rods are those rods that we bring down to absorb neutrons to control or stop the reaction. And we normally use metals such as cadmium for that. Now, fission reactions can create tremendous amounts of energy simply by looking at Einstein's equals mc equation when we're looking at the mass defect of what's happening when the fission process occurs. So according to Einstein, a nuclear reaction mass is not conserved. The difference of mass must be because some of the mass is converted to energy. So here's a question for you. What is the difference between fuel and spent fuel? Is it A, fuel is rich in cesium and the spent fuel is not? Is it B, spent fuel is rich in uranium and the fuel is not? Is it C, the mass of the spent fuel is less than the mass of the fuel? Or is it D, the mass of the fuel is less than the mass of the spent fuel? Well, in this case, the mass of the spent fuel must be less than the mass of the fuel. And that's why there's so much energy given off, because of the mass difference. The mass change or the mass defect is the energy of what's happening. So now let's try and find the energy produced by nuclear fission of uranium-235. So in this case here, we have uranium-235 reacts with a neutron. So a neutron is being shot into uranium-235 to produce barium-144 and krypton-36 and then 3 more neutrons. We want to determine the energy of this reaction. Well, my information is given here up above. So I'm going to use that information to help me. Now remember, when we're looking at this, we're going to be looking at my mass defect. So first, I want to find my initial mass, which is going to be my mass of the uranium-235 plus my mass of the neutron, which is going to be, from my information above here, 3.929 times 10 to the negative 25 plus 1.67 times 10 to the negative 27. And when I add that together, that's going to give me 3.19194649 times 10 to the negative 25 kilograms. Now, let's find my mass of my products. So here we're going to look at the mass of barium-144, which is 2.3898 times 10 to the negative 25, plus the mass of krypton, which is 1.4765 times 10 to the negative 5, plus 3 times the mass of my neutron. Now, when I add these all together, I'm going to get 3.196547 times 10 to the negative 25 kilograms. So now that I have my two masses, I'm going to subtract these masses to get my mass defect. And then from there, I can figure out my energy. And that's going to end up giving me 3.102 times 10 to the negative 25 kilograms. So now that I have my mass defect, I can end up finding my energy by using my energy is equal to mass, my change in mass, or my mass defect, times the speed of light squared. So my mass defect was 3.102 times 10 to the negative 25 kilograms, and we're going to times that by the speed of light squared, which will end up giving me 2.791 joules. So once again, nuclear fusion is the exact opposite of nuclear fission. So instead of separating atoms into smaller atoms, what we're doing is we're combining small nuclei into a larger atom. So where we see fusion is in the sun, and that's the only place where we're getting useful energy from fusion so far. Well, we have used fusion, but not really in a positive way, as we've only really been able to use it in the hydrogen bombs. Now, let's take a look at a fusion energy conversion here. So I want to know what is the energy that's going to be converted from this fusion. So here we have deuterium hydrogen and tritium hydrogen being fused together to produce helium and a neutron. So once again, we have to find our mass defect. So first we must know our initial mass, which is going to be the deuterium hydrogen plus the tritium hydrogen. Now, by looking up, I could find the masses of both of those. The mass for the deuterium hydrogen is going to be 2.014102 atomic mass units. And my mass of my tritium hydrogen is going to be 3.016049 atomic mass units. When I add these together, I'm going to end up getting 5.030151 atomic mass units. Now let's look at my final, the mass of my final product. So here we have a helium, so we want the mass of a helium, and then we're going to add the mass of a neutron. So in this case here, we know the mass of helium is going to be 4.002603 atomic mass units. And we know the mass of a neutron is 1.008665 atomic mass units. So we're going to end up getting 5.011268 units. Now let's look at my mass defect. My mass defect is going to be my initial mass minus my final mass, which we're going to end up getting 5.03151, and we're going to subtract 5.011268, which will give me a total of 0.018883. Now, if we want to make this, we're going to use this one in electron volts. I'm just going to times it by 931.5 electron mass, electron volts over my units. These will cancel off, and that's going to end up giving me 17.59 mass electron volts. So some of you may be a bit confused and have this question: how is it that when I combine some elements, we have a mass defect and therefore we get energy, while as when we separate other elements, we have a mass defect and create energy? So how can we have energy from both fission and fusion? Well, this graph here will help clarify that. We have my y-axis is describing the amount of energy per nucleon, and my x-axis is telling me how many nucleons are in the nucleus. Now if we look at this here, iron is my apex of this curve, meaning it's the top of the curve. So the most energy per nucleon is going to be your most stable element, which happens to be iron. So now all atoms want to become stable. Iron is the most stable. So if we look at the atoms on the left, they are going to undergo fusion because they are small and they need to become bigger atoms in order to be stable. So all these on the left are going to move up the curve until they hit iron, because remember, our apex is the most stable. My y value, when it's the highest, is the most energy per nucleon, which means it will be the most stable. Now if we look to the right, we're going to undergo fission, because these ones here are also below the binding energy per nucleon than iron. So all of these here are going to end up going through fission to become iron. So they're actually going to become smaller. If we look, they're going to reduce the amount of nucleons and become smaller in order to become more stable. So those ones are going to separate. Now here's something interesting to look at between these. If we look at the slopes of my first half here, we have an extremely steep slope. For instance, if I look at two deuteriums, which is a hydrogen with a neutron, and they combine or fuse together to create helium, I end up having a huge steep slope here. My x, or number of nucleons, barely shifts over compared to the amount of increase I get in the y for binding energy when we have fusion of two deuteriums into helium. My slope and my jump to go from two deuteriums to helium is huge. That means there's going to be a lot of energy given off there to get that stability. So let's compare that to the fission of uranium. Remember, uranium is going to be on the right side, so it's going to undergo fission, where it's going to separate to become smaller in order to reach iron, which is a smaller element. So if I look at uranium here, and uranium breaks down to krypton and baryon, which is somewhere right here, my Y increases here are not going to be even nearly as great as my Y increase from deuterium to helium. So according to this graph, it may seem like fusion is a lot easier or should naturally happen faster than fission, but it doesn't. The thing that makes fission so easy to control and harness the power is we could create chain reactions fairly easily with fission. If we remember from earlier in this video, we learned that in a fission of uranium, 3 neutrons are going to be separating out and shooting out as well, reacting with other uraniums, causing more and more fission, which eventually allows it to go to iron. And we could actually control these neutrons, which provocate fission reactions. Whereas we are unable to really control anything on the fusion side. So because fusion seems to have so much potential for energy and we are unable to harness it yet, there is a lot of research being done with regards to fusion energy. Now, nuclear fusion is an important natural process. Many chemical elements originate from hydrogen and then they fuse together and become what they are now through the process of fusion. Fusion, after all, is the energy source of the sun and stars. So how powerful is fusion fuel? Well, if we can learn how to harness it, we could then harness 1 gram of fission fuel will generate 90,000 kilowatt hours of energy in a power plant, which is equivalent to 11 tons of coal.